The goal of this video is to explain what normal forms are in propositional logic, specifically disjunctive normal form and conjunctive normal form. By the end of this video, you should be able to define what a normal form is, identify formulas that are in normal form, take formulas that are not in normal forms and transform those into those that are in normal forms, as well as look at a truth function or truth table and construct a formula that is in normal form that expresses that function. The first thing that you need to know is what a normal form is, but for that, I think it's helpful to define a couple key terms first. That first term that we need to have an understanding of is what a literal well-formed formula is. So let's dive into that, and then we'll come back and talk about some other terms that we need in order to have a clear sense of what a normal form is in propositional logic. A literal well-formed formula in propositional logic is either a propositional letter or a negated propositional letter. Let's look at some examples of literals. So P, Q, R. Notice all these are propositional letters, and so they would be literals. Not P, not Q, not R, as well as not S. Notice that these are negated propositional letters, and so they also would be literals. Some formulas that are not literals include P right arrow Q. So notice this is not a literal because it is neither a propositional letter nor a negated propositional letter. P or Q, P and Q. And finally, not P is also not a literal because it is not a propositional letter and it is not a negated propositional letter. This is a negation of a propositional letter. Welcome back. So now that you know what a literal well-formed formula is, the next thing that we need to know in order to understand what a normal form is what an elementary disjunction and an elementary conjunction is. So the next step is to define what an elementary disjunction is and be able to identify formulas that are elementary disjunctions. So let's take a look at that. Let's take a look at the definition of an elementary disjunction in propositional logic. So a formula is an elementary disjunction provided it has the form a sub 1 or a sub 2 all the way up to a sub n, where n is a number greater than or equal to 1, and where each one of those a's is a literal well-formed formula. So let's look at some examples. Let's start with cases where n is equal to 1. That is, we're simply looking at a formula. So what we're doing here is looking at a formula where it's just a sub 1. It doesn't necessarily need to be a disjunction. So in order for a formula to be an elementary disjunction, it needs, as the definition states, to be a literal well-formed formula. So what this would mean would be that P, not Q, R, not S, all of these formulas, which are literal well-formed formulas, are also elementary disjunctions. In short, single propositions can be elementary disjunctions, even though they are not disjunctions, provided they are literal well-formed formulas. Now let's look at a case where n is greater than 1. So in this case, what we would need is a formula of the form a sub 1 or a sub 2, and it could be larger. It could go all the way up to a sub n. The condition associated with elementary disjunctions is that each one of these a's, each one of these formulas, needs to be a literal well-formed formula, and each one needs to be connected using a disjunction. In other words, each one of the disjuncts of a elementary disjunction needs to be a literal well-formed formula. Let's look at some examples. So P or Q, notice this has the form a sub 1 or a sub 2. It's a disjunction. And since each one of the disjuncts is a literal well-formed formula, this would be an elementary disjunction. Next, let's take a look at P or Q or not R. Notice again, this is a disjunction, and each one of the disjuncts is a literal well-formed formula, so this too would be an elementary disjunction. Let's look at one more example. Let's say we had P or not Q or not R or not S. Notice that this formula has the form a sub 1 or a sub 2 or a sub 3 or a sub 4. Also notice that each one of the disjuncts of this disjunction is a literal well-formed formula. So you could go through each one and see, oh, this one's a literal, this one's a literal, this one's a literal. And so what we have here is also a elementary disjunction. Let's look at two formulas that are not elementary disjunctions. So first, let's look at P right arrow Q. If we took P right arrow Q and treated it like a single formula, in order for it to be an elementary disjunction, it would need to be a literal. But since it is not a literal well-formed formula, this formula is not an elementary disjunction. Now you might say, well, maybe this formula can be of the form a sub 1 or a sub 2. If it were, and a sub 1 and a sub 2 were composed of literals, then it would be an elementary disjunction. You could point to the fact that P is a literal and Q is a literal. The problem is that in order for it to be an elementary disjunction, it actually needs to be a disjunction. But notice that this formula right here is a conditional, and so in this case, it would also not be an elementary disjunction. So P right arrow Q here is not an elementary disjunction. Let's look at one more example. Let's say we had not P or Q. If we had not P or Q, we might be tempted to say, well, look, this formula has the form a sub 1 or a sub 2. The problem with this idea is the fact that the formula is not composed of literals. Not P here is not a literal. And since it is not a literal well-formed formula, it is not a disjunction composed exclusively of literals. And so it would not be an elementary disjunction. Welcome back. So now that you understand what an elementary disjunction is, it's now time to look at what an elementary conjunction is. Now, if you understood what an elementary disjunction is, then this is not going to be too difficult for you. After we looked at what an elementary conjunction is, then we'll be ready to define when a formula is in normal form. An elementary conjunction is a propositional logic well-formed formula of the form a sub 1 and a sub 2 and a sub n, where n is greater than or equal to 1, and where each one of those a's are literal well-formed formulas. Let's look at some examples. Let's start by looking at a case where n is equal to 1. That is, we're looking at a formula that is simply a proposition. In order for simply a formula or proposition to be an elementary conjunction, we see that it has to be a literal. So what this means is a formula like P, not Q, R, not S, all of these would be elementary conjunctions. And again, the reason is they are a formula, and that formula is a literal. Let's look at a case where n is greater than 1. So this would be a formula of the form a sub 1 and a sub 2 and all the way up to a sub n. And each one of these a's needs to be a literal well-formed formula. So if we had, let's say, not P and Q, we'll notice that each one of these conjuncts is a literal well-formed formula. And so this would be an elementary conjunction. Also take a look at, let's say, not P and not Q and not R. Notice each one of these conjuncts is a literal well-formed formula. And so this also would be an elementary conjunction. Let's look at one more example. Let's say we had P and Q and not R and not S. Well, notice that this formula has the form a sub 1 and a sub 2 and a sub 3 and a sub 4. And notice that when we look at each one of the a's, each one of the conjuncts of this formula, we see each one is a literal. And so that would mean that this particular formula is also an elementary conjunction. Let's look at some examples of formulas that are not elementary conjunctions. A simple case would be P right arrow Q. P right arrow Q is not an elementary conjunction. And the reason for this is because if we treat it as a single formula, a sub 1, then it is not a literal. And remember, in order for a single formula to be an elementary conjunction, it needs to be a literal formula. But since this is not a literal formula, it's not a propositional letter or its negation, then it is not an elementary conjunction. One thing that you might say is, well, look, P is a literal and Q is a literal. Why isn't this an elementary conjunction? The answer here is if we treat it as the form a sub 1 and a sub 2, one thing that we see is that the formula is not a conjunction. Notice the main operator here is this right arrow, whereas in order for it to be an elementary conjunction, it needs to be a conjunction of literals. So this would not be an elementary conjunction because the formula is not even a conjunction. Let's look at one more example. Let's say we had not P. Well, this particular formula would not be an elementary conjunction. The rationale is the same. If we treat it as a single formula, well, since it's not a literal, then it is not an elementary conjunction. Or if we said that it has the form a sub 1 and a sub 2, well, the first thing to note is that this particular formula here is not a conjunction. And so since it is not a conjunction of literals, this formula here would not be an elementary conjunction. So not P is not an elementary conjunction. Welcome back. Now that you understand what it means for a formula to be a literal well-formed formula, as well as an elementary conjunction or elementary disjunction, it's now actually time to define what it means for a formula to be in normal form. We'll start by looking at what it means for a formula to be in disjunctive normal form first. So let's hop into that. A well-formed formula is said to be in disjunctive normal form when it has the following form. It is a formula a sub 1 or a sub 2 or all the way up to a sub n, where each one of these a's, each one of these formulas is an elementary conjunction. So it is either a literal or a conjunction of literals. Now let's take a look at some examples. Let's start by thinking about cases where n is equal to 1. So this is a case where we're just looking at a single formula, a sub 1. It doesn't need to be a disjunction. And asking ourselves, is this formula in disjunctive normal form? Well, our answer would be yes, just in the case that that formula is an elementary conjunction. So we would only say yes if a sub 1 here is an elementary conjunction. In other words, that a sub 1 needs to be one of two formulas. It needs to either be a literal well-formed formula, so it needs to be a literal, or it needs to be a conjunction of literals. So let's take a look at some quick examples of each one. So if you had a formula like P or not Q or not S, all of these are literal well-formed formulas. These formulas would be elementary conjunctions, and so they would be in disjunctive normal form. If you had a formula like P and Q, or you had, let's say, not P and not Q, these two formulas here are conjunctions of literals, and so they would also be in disjunctive normal form. So if you have a formula that is a literal or a conjunction of literals, then that formula is in disjunctive normal form. What about a case where n is greater than 1? So we wouldn't just be looking at a single formula and saying, independent of its structure, is it in disjunctive normal form? Instead, we'd say, well, is this formula that has the structure a sub 1 or a sub 2 or all the way up to a sub n, is that formula in disjunctive normal form or not? The answer to this would be yes, provided you have a disjunction of elementary conjunctions. So if you had elementary conjunction or elementary conjunction 2 or elementary conjunction 3, all the way up to, let's say, elementary conjunction n, provided you have a disjunction where each one of these disjuncts is an elementary conjunction, then your formula would be in disjunctive normal form. Again, remember, each one of these disjuncts needs to be either a literal well-formed formula, or it needs to be a conjunction of literals. So let's take a look at some examples. Let's say we had the formula P or Q. This is a real simple example here. We'll take a look at this formula. It definitely is not a conjunction of literals, but one thing to notice is that it has the structure a sub 1 or a sub 2. So it's a disjunction. And we can ask ourselves, is it the case that each one of these disjuncts, P, Q, is either a literal or a conjunction of literals? In other words, is each one of these disjuncts an elementary conjunction? And the answer to this would be yes. And so it would be in disjunctive normal form. We see that P is a literal, and so it is an elementary conjunction, and Q is a literal, so it is also an elementary conjunction. And since you have a disjunction of elementary conjunctions, the formula is in disjunctive normal form. Let's look at another example. Let's say we had not P or not Q or R. So one way of looking at this is, look, what we have here is 3 elementary conjunctions. And notice that all 3 of them are connected using this sign for disjunction. So you have a disjunction of elementary conjunctions. And so this also would be in disjunctive normal form. Let's look at another example. So let's say we had not P and Q or S and T. The question is if this is in disjunctive normal form. Now, if you look at this formula is in disjunctive normal form in one of 2 cases. One is if it is an elementary conjunction. Well, the formula is not an elementary conjunction, so that case wouldn't apply. The other case would be if it is a disjunction of elementary conjunctions. So if each one of these is, each one of the disjuncts is an elementary conjunction, then it would be in disjunctive normal form. Well, when we look at it, what do we see? Well, we have a disjunction, and both of the disjuncts are elementary conjunctions. And so, yes, this would be in disjunctive normal form. Let's finish off with a couple examples of formulas that are not in disjunctive normal form. So let's start with some simple cases. Let's say you had P right arrow Q. Now, the first question you might ask is this formula an elementary conjunction? The answer to this is no. It is not a literal well-formed formula, and it is not a conjunction of literals. The second question you could ask is this a disjunction of elementary conjunctions? The answer to is no. This is not even a disjunction. Notice that you have this sign for conditionality right here. And so since the answer to both questions is no, this would not be in disjunctive normal form. Let's look at another case. Let's say we had the formula P or Q and R. So the question is this formula in disjunctive normal form? Again, we could ask ourselves the same 2 questions. First, is it an elementary conjunction? And when we look at it, we'd say, no, it's not, because this left conjunct here is not a literal well-formed formula, and you don't have a conjunction of literals, so the answer to this would be no. The next question you can ask is it a disjunction of elementary conjunctions? And the answer to this also is no. So why is that no? It's no because take a look at the main operator here, which is the sign for conjunction. So it doesn't have the form a sub 1 or a sub 2. And so this formula would not be in disjunctive normal form. As a final exercise, take a look at these 8 formulas. My challenge to you is to look through each one of these formulas and determine whether or not they are in disjunctive normal form. I'd love to hear your answers in the comments below. And if you have any insights about how you think about disjunctive normal form, I'd love to hear those as well. Welcome back. So now that you know what it means for a formula to be in disjunctive normal form, it's now time to look at what it means for a formula to be in conjunctive normal form. A well-formed formula is said to be in conjunctive normal form when it has the following form: a sub 1 and a sub 2 and a sub n, where each one of these, a sub 1, a sub 2, a sub n, is an elementary disjunction, and where you at least have one formula. So let's start by looking at a case where n is equal to 1. So in other words, we have a formula and we're asking ourselves, is this formula in conjunctive normal form? And the formula does not necessarily need to be a conjunction here. So it doesn't need to have the form a sub 1 and a sub 2. We're just asking for a given formula, whatever it might be. Can this formula be in conjunctive normal form? The answer for that is yes, provided that formula is an elementary disjunction. So a sub 1 can be in conjunctive normal form provided it is an elementary disjunction. What this means is that formula either needs to be a literal well-formed formula, or it needs to be a disjunction of literals. Let me give you examples of each. So in the case of the literals, if we had a formula like P, not Q, or R, well, then these formulas would be in disjunctive normal form because they are literal well-formed formulas. And since they're literal well-formed formulas, they're elementary disjunctions because all literals are elementary disjunctions. And since it is an elementary disjunction and it has the form A1, it is a single proposition or formula, then it is in conjunctive normal form. The other case would be if you have a formula, it's an elementary disjunction, and that elementary disjunction is a disjunction of literals. So let's say you had P or Q. This is a disjunction of literals. So you have P here and Q. Each one is a literal and it's a disjunction of them. And so this would be an elementary disjunction. And so this disjunction is actually in conjunctive normal form. Another example would be not P or S or not T. This formula is a disjunction of literals, and so it's an elementary disjunction, and so it is a formula in conjunctive normal form. So if we're looking at a single formula and asking ourselves, is this formula in conjunctive normal form? The answer would be yes, provided you are looking at a case of a literal well-formed formula or a disjunction of literals. Now, what about the case where n is not equal to 1? So we're not looking at a single formula, but n is greater than 1. So we're looking at a formula that has the form, let's say, a sub 1 and a sub 2 and all the way up to a sub n. So we're actually looking at a conjunction and asking ourselves, is this formula in conjunctive normal form? Well, the answer to this is yes, provided we have a conjunction of elementary disjunctions. So if we had a conjunction where we have elementary disjunction 1 and elementary disjunction 2 and all the way up to elementary disjunction n, so provided we have a conjunction where each one of the conjuncts, each one of these subformula here are elementary disjunctions, then it would be in conjunctive normal form. Again, each one of those elementary disjunctions is either a literal, so it's a formula like P or not P, or it is a disjunction of literals. Let's take a look at some examples. Let's say we had P and Q. When we look at this formula, one thing that we see is, look, it is a conjunction and it has the form of a sub 1 and a sub 2. Now, is it the case that P, which is our a sub 1 here, and Q, which is our a sub 2 here, is it the case that P and Q are elementary disjunctions? That is, are they literals or are they disjunctions of literals? The answer here would be yes. They are elementary disjunctions. And so we have a conjunction of elementary disjunctions. And so this formula would be in conjunctive normal form. Let's look at another example. Let's say we had not P and not Q and R. So our question again is this in conjunctive normal form? First thing to note is that our formula has the following structure: a sub 1 and a sub 2 and a sub 3. So our question becomes, is each one of the conjuncts in this formula an elementary disjunction? That is it a literal or a disjunction of literals? And so if we look, not P is a literal, not Q is a literal, R is a literal. And so each one of these conjuncts is an elementary disjunction. And so this formula would be in conjunctive normal form. So let's say we have the formula not P or Q. So we have this disjunction here, and then we had and, S or T. Now, one way of going about this is to ask ourselves two different questions. The first question would be, if we treat this whole thing as a single formula, is this formula an elementary disjunction? So is this whole thing an elementary disjunction? The answer to that is no, it is not. And so from that fact, we cannot conclude that this is in conjunctive normal form. If it were an elementary disjunction, that is, if it were a disjunction of literals or it were just a literal, then we could conclude it is in conjunctive normal form. The other question we can ask ourselves is, well, let's take a look at the structure of this formula. And one thing to note is we see that it is a conjunction. And it's a conjunction of two different formulas. So we can look at it as a sub 1, which is the left conjunct here, and a sub 2, which is the right conjunct there. Now that we see that this is a conjunction, is it a conjunction of elementary disjunctions? That is, do we have ED1 and ED2? That is this formula right here an elementary disjunction, and is this conjunction here an elementary disjunction? If this conjunction is composed of two elementary disjunctions, then it would be in conjunctive normal form. So we see that yes, not P or Q is a disjunction of literals, and so it is an elementary disjunction. And then S or T is also a disjunction of literals, so it too is an elementary disjunction. So we have a conjunction that is composed of two elementary disjunctions. And so yes, this is a conjunction of elementary disjunctions, and so it also is in conjunctive normal form. Let's look at some examples of formulas that are not in conjunctive normal form. So let's take a look at the formula P right arrow Q. Now we could of course ask ourselves the two questions, which would be first, is this an elementary disjunction? The answer to that would be no, it is not an elementary disjunction because it's not a literal, and then also it is not a disjunction of literals. The second question would be, well, is this formula a conjunction of elementary disjunctions? The answer to that is also no. This formula is not a conjunction at all. Notice that there is the sign for conditionality right there. And so this is a conditional rather than a conjunction. And so from this fact, we can conclude that this formula is not in conjunctive normal form. Now let's take a look at this formula, P and Q or R. Again, one way of approaching whether or not this formula is in conjunctive normal form is to first ask ourselves, is it an elementary disjunction? That is, if we just treat it like a single formula, is it a literal or a disjunction of literals? Now, the right disjunct here is a literal. This R here is a literal, and it is a disjunction, but notice that it is not a disjunction of literals because we have this P and Q here. It's a disjunction of R and a conjunction. So the answer to this would be no. And so this formula would not be an elementary disjunction. Again, the second question we can ask is this formula a conjunction of elementary disjunctions? If it is, then we can say it is in conjunctive normal form. However, when we look at this formula, we see that it is not a conjunction. In fact, it is a disjunction here. And so we can say also that this is not a conjunction of elementary disjunctions. And since we can answer no to both of those questions, this formula is also not in conjunctive normal form. So my challenge to you is to look through these 8 formulas right here and determine which of the 8 formulas are in conjunctive normal form. I'd love to see your answers in the comments below, or if you have any insights about how best you think about or understand conjunctive normal form or normal forms in general, I would love to read those as well. Welcome back. Now that we have a clear sense of what it means for a formula to be in disjunctive normal form and conjunctive normal form, let's talk about how we can take a formula that is not in either one of those forms and transform it into a formula that is either in disjunctive normal form or conjunctive normal form. So let's talk about how you can take a formula and transform it into a formula that's either in conjunctive normal form or disjunctive normal form. The way that we'll do this is we'll look at formulas and then we'll take that formula and use equivalence rules to transform it into a formula that is in one of the two types, or sometimes both, in conjunctive normal form or disjunctive normal form. So how do we do that? What we're going to do is use these rules over here on the left-hand side. So all of these are equivalence rules, these rules 1 through 13. The way you read these rules is that you can take a formula on, let's say, the left-hand side or the right-hand side and replace it with the formula on the other side. So for example, number 1 here, we have not P, this doubly negated formula. We can replace it with P, or we could take P and replace it with not P. One more quick example. Let's take a look at 6 here. So 6 is association. we have this conjunction where it's P and Q and R, and we can use the association rule to replace it with P and Q and R. But notice that we move the parentheses from being originally around Q and R to being around P and Q. So we're going to use a bunch of equivalence rules that we have over here, equivalence rules, to transform a formula that is not in conjunctive normal form into, or disjunctive normal form, into one that is in conjunctive normal form or disjunctive normal form. So how do we do this transformation? Well, we use a three-step process. The first step is to use equivalence rules to replace formulas that have the right arrow or the double arrow. And once we've done this, we will be left with a formula that the only operators it can have are negation, conjunction, or disjunction. So which rules are we going to use to do this? The rules we'll use are implication. You can take a look at that at line 10, which takes this conditional and turns it into a disjunction. So that will allow us to remove this right arrow, and this biconditional equivalence rule, which will allow us to take this biconditional and replace it with a conjunction of conditionals. And then we can use the implication rule from 10 to remove those right arrows. So what we're going to do is use rules 10 and 11. So what about step 2? So step 2, sometimes people characterize it as you should try to push the negations inward. Now, what does this mean? Well, what we're going to do is use De Morgan's laws in order to do this. And at the end of this, what we will be left with, which is a formula, and that it only will have some combination of these three operators, but there won't be any formulas where the negation is on the outside. So there won't be a formula like that is a negated disjunction or a negated conjunction. Let's take a look at this De Morgan's laws really quickly. So you see De Morgan's laws, it'll take a formula that has the negation on the outside, either negating a disjunction or negating a conjunction, and replace it with, in the case of the negated disjunction at rule 8, it'll replace it with a conjunction where the conjuncts are now negated. In the case of rule 9 here, notice that we're taking a negated conjunction and transforming it into a disjunction where both of the disjuncts are negated. So as I mentioned, after we use De Morgan's laws a sufficient number of times, we won't have any formulas of this variety. This takes us to our final step, step 3, and step 3 is generally to use distribution. You'll use distribution in order to get a formula that's in conjunctive normal form or disjunctive normal form. Now, in the process of using distribution, you may need to use some other rules. You may need to use double the negation rule. You might have to use the idempotence rule. You might use commutation. So you might use some other rules in order to use distribution. And the result of all this will give you a formula in conjunctive normal form or disjunctive normal form. So let's start with the formula not P, right arrow Q. So we have this negated conditional. Now step 1 says to try to use an equivalence rule that removes that right arrow. And the rule that we'll use is implication. Now I'll briefly show you what the implication rule looks like up here, but you want to become familiar with the equivalence rules yourself. So implication says if we have a conditional, P right arrow Q, we can replace it with a disjunction, not P or Q. And so what we're doing is taking P right arrow Q and then replacing it with not P or Q. Now I'm just going to write implication off to the side here just so it's clear that I used implication on the prior formula in order to get this formula here. Now that we'll proceed to the second step. Now, if you remember what the second step is, it says push those negations inward, and you'll use De Morgan's laws to do that. So let's do that. Let's take De Morgan's laws, and De Morgan's laws will give us not P and not Q. This is by using De Morgan's laws. Okay, so we have a formula, but it's not quite in either conjunctive normal form or disjunctive normal form. The last thing we need to do is kind of clean up this formula. So if you see step 3, it says distribution, but you may also need to use things like double negation, commutation, idempotence. So in our case, we are going to take this not P and remove those two negations using the double negation equivalence rule. That will give us P and not Q, and we use double negation in order to get it. At this point, we have a formula that is in both conjunctive normal form and disjunctive normal form. Let me briefly illustrate that. So we have P and not Q. Well, the first thing to note about this particular formula is that we have a conjunction, A1 and A2. And notice that both of the conjunctions are elementary disjunctions because they're literals. And since we have a conjunction of elementary literals, we have a formula in conjunctive normal form. The second thing to note is that this is a formula, and this whole formula here is an elementary conjunction. It is a conjunction of literals. And if you have just a conjunction of literals, that is a single elementary conjunction, then the formula is in disjunctive normal form. So this formula, P and not Q, is both in disjunctive normal form and in conjunctive normal form. Let's look at another example. In this case, let's take a look at not P or Q and R. So the first thing to note is that there's not a right arrow or a sign for biconditionality, and so we don't need to use step 1. Instead, we can proceed immediately to step 2, which is to push those negations inward by using De Morgan's laws. So if we use De Morgan's laws, it will give us the following formula. It'll turn this disjunction into a conjunction. The next thing to note is we can use De Morgan's laws again. This time we're going to use it on the right conjunct. And this will give us not Q or not R. This is also by De Morgan's laws. At this point, you might consider stopping because take a look. This formula is in conjunctive normal form because if you take a look at it, it is a conjunction as the form A1 and A2. And both of those conjuncts are elementary disjunctions. So you have this A1, which is not P, is an elementary disjunction. And then you have not Q and not R here, which is also an elementary disjunction. And so you have a conjunction of elementary disjunctions. And so you have a formula in conjunctive normal form. So if you were only trying to get a formula in conjunctive normal form, you could stop here. But if you also wanted it in disjunctive normal form, then you would need to proceed to step 3, which is to apply the distribution rule. So if we use distribution, what it will give us is not P and not Q, or not P and not R. Now the thing to note is that this formula is in disjunctive normal form. Notice the structure of it is A1 or A2. And we can see that A1 here is an elementary conjunction. So we have not P and not Q. It's a conjunction of literals, or not P and not R, which is also an elementary conjunction. So we have a disjunction of elementary conjunctions. And so this is in disjunctive normal form. Let's look at one final example. So in this final example here, we'll look at the formula A and not B, or not A and B. So the thing to note about this one is that it is already in disjunctive normal form. Notice you have a disjunction of 2 elementary conjunctions, and so it is in disjunctive normal form. But let's say we wanted to take this formula and transform it into one in conjunctive normal form. Well, we don't need to do step 1, which is to remove any right arrows or biconditionals. And we don't need to do step 2. We don't need to push any negations inward. Instead, we'll start with step 3, which is to use the distribution rule. Let's use distribution. And if we use distribution on this formula, it will give us A and not B, or not A, and A and not B, or B. This is what happens when we use distribution. We still don't have a formula in conjunctive normal form, so we're going to use distribution again on each one of these conjuncts, the left conjunct and the right conjunct. I'm going to clean things up a little bit to make it maybe easier to see how distribution is used. And I'm going to use the commutation rule, which is going to allow me to sort of move this not A to the left-hand side and move this A and not B to the right-hand side. So I have this disjunction here, and so I'm just going to rearrange this a little bit just so the distribution rule is easier to see. I'm writing B or A and not B. And so I've just kind of swapped these disjuncts around using commutation. So the last step here will be to use distribution again, and I'm going to use it twice, one on each conjunct. Using distribution will give me not A or A, and not A or B, and B or A, and B or not B. And so this was by distribution. We have quite a mess here, but take a look. We have a formula of the form A1 and A2 and A3 and A4. Now, this formula would only be in conjunctive normal form if A1, A2, A3, and A4, which are all conjuncts, are elementary disjunctions. Well, notice that each one of these is an elementary disjunction. And so this formula is in conjunctive normal form. As a final kind of exercise, try to take these three formulas and transform them into formulas that are in conjunctive normal form and in disjunctive normal form. I'm interested to know especially your answer to this first one right here. So let me know what you come up with in the comments below. Welcome back. Now you should know how to take a formula and transform it into a formula that's in either disjunctive normal form or conjunctive normal form. Next, let's talk about how you can look at a truth table and use that table to construct a formula that expresses that table, that is, expresses the function that is represented in that table. We'll start with disjunctive normal form. So what we're going to do is look at a couple truth tables and talk about the process that you would use to take that table or the function that's expressed by that table and construct a formula that expresses that function. So let's look at how to create a formula in disjunctive normal form from a truth function. As a preliminary, let's briefly talk about how you can represent a truth function with a formula. And then we'll circle back to how you would represent it using a formula in disjunctive normal form. So the first thing that you'll want is a truth function, and truth functions are often represented using truth tables. So let me create a quick table right now. Looking at this truth table, what we want is a formula that is true just in the case where the interpretation of A, that is the truth value assignment to A, is true, and when the interpretation of B, that is the truth value assignment of B, is true, and where it's going to be false in all of the other cases. So what we want to know is a formula that is true just in the case that A is true and B is true. Well, one such formula is A and B. And so we can see that this formula takes a value of true just in the case where A is true and B is true. And this formula would also be false in all other cases. So if it has any other truth value assignment, then this formula comes out as false. So we can express the fact that this particular function is true under this assignment using a conjunction, where we write the literal A and the literal B and create a conjunction from those two. Now, the thing I want to point out is the fact that this particular formula is true just in the case that A is assigned a value of true and B is assigned a value of true. Let's look at another example, and I'll create another truth table. So again, what we want here is we want a particular formula that is true just in the case where A is assigned a value of true and where B is assigned a value of false. Since we need a formula that is true just in this one case, just in the case where A is true and B is false, what we can do is write the literal A and not B. Now this particular formula will be true just in the case where A is true and B is false. So if you did the little truth table here, you would see that this formula comes out as true. But let's look at a different case, and I'm going to create one more table. Now notice in this example, this particular formula is true in two cases. In the case where A and B are assigned a value of true, and the case where A is assigned a value of true and B is assigned a value of false. So what we want is a formula that comes out as true just in two cases. The first case is the case where A is assigned a value of true and where B is assigned a value of true, or in the case where A is assigned a value of true and B is assigned a value of false. Okay, so that's clear enough from the table. Now remember that we have a way of expressing a formula that is true just in the case where A is true and B is true. And we said that we look at the row of the truth table and we write A and B. So if the truth value assigned to A is true, then we write the letter A. And if the truth value assigned to B is true, then we write the letter B. We also noted that there is a way of constructing a formula when A is assigned a value of true and B is assigned a value of false. For that case, what we did was we created a conjunction where since A is true, we just write A, and where B is false, we will write not B. So we write the single propositional letter if it's assigned a value of true, and we write the negation of that propositional letter if it is assigned a value of false. Now, each one of these formulas are true just in one case. The first one is true just in the case where A and B are true, and the second one in the case where A is true and B is false. Now we can use these two formulas to express this function here, a function that outputs a value of true in two cases, by creating a disjunction of those two formulas. The first formula is true just in the case that A and B are assigned the truth values from row 1, and the second formula is true just in the case that A and B are assigned truth values from row 2. And by creating a disjunction of the two formulas, we can express this function which outputs a value of true in either one of those two cases. Now I want to go back to our formulas and point something out. So in the first example here, this A and B, which expresses this function here, note that it is an elementary conjunction. It is a conjunction of literals, and since all elementary conjunctions are in disjunctive normal form, this particular formula is in disjunctive normal form. In other words, what we've done is we've looked at this table and created a formula that is in disjunctive normal form, which is what we're trying to do. Let's look at the second table. Notice again that this particular formula, A and not B, is an elementary conjunction. And since it is an elementary conjunction, this particular formula is also in disjunctive normal form. And again, what we've done is we've taken this truth function here and we've expressed that truth function in terms of a formula that is true whenever the function is true. So it captures this function. Now let's look at our third case here. In our third case here, we created a formula, and it's this big long disjunction here. Now this formula is not an elementary conjunction, but it is in disjunctive normal form. The reason is because this formula is a disjunction of elementary conjunctions. And if a formula is a disjunction of elementary conjunctions, then it is in disjunctive normal form. So what we've done again is we've looked at this table and expressed the truth function here, the function expressed by this table, in a formula. I want to briefly state the process by which you would construct a formula in disjunctive normal form from a truth table. So step one. Step one is you identify each row where the output of the function is true. So identify each row of the truth table where the function outputs true, where the function outputs, let's say, a 1 or a truth value of t. Step two is for each row. So for each row where the output is true, you will create a conjunction of literals. So we'll create a conjunction of literals. And we'll create the conjunction in the following way. We will simply write the propositional letter. So we'll write P if the interpretation or truth value of assignment to P is true. And we'll write not P, which is the negated propositional letter, if the interpretation of P is false. So if P gets a value of 1, then we'll simply write P. And if P is assigned a value of false, then we'll write not P. And then the last step here, step 3, will be to create a disjunction of all of the conjunctions. So here we have a truth table, and what we'll do is step 1 will be to identify where the function outputs a value of false. This would be rows 1, 2, and 4. Then step 2 will be to create a conjunction for each row. So we would create A and B. We'll write the propositional letter when it's assigned a value of true, and the negation of the propositional letter when it's assigned a value of false. So we'll write A and not B for row 2. And then row 4, we'll write not A and not B. And the reason for that is because A and B are assigned a value of false. And then step 3 is to create a disjunction for each one out of each one of these conjuncts. So we would write A and B, which is our conjunction from row 1, or A and not B, which is our conjunction from row 2, and then or. So this is the last conjunction here, not A and not B, and we would be done. We would have a formula in disjunctive normal form, which is true just when the function outputs a value of true. Welcome back. So now let's talk about how you can take a table and use that table to construct a formula in conjunctive normal form that expresses the function represented by that table. Let's look at how to construct a formula in conjunctive normal form from a truth table. So again, the first thing that we're going to need is a truth function or truth table. So I'll write that out really quickly. So here's our truth table. We have an input or truth value assignment to A and B, and we have an output, which we can see under the column for F. The first step to getting a formula in conjunctive normal form is to identify the false rows, the rows where the function is false or outputs a value of false. So in our case, this would be rows 2 and 3. For each row where the function outputs a value of false, we'll create a conjunction of literals. And that conjunction of literals will consist of the propositional letter A, if the truth value assigned to A is true, and we'll write the negation of the propositional letter if the propositional letter is assigned a value of false. So notice in the second row, since A is assigned a value of true, we simply write A, and B is assigned a value of false or 0, so we write not B. In the third row here, we see that A is assigned a value of false, so we'll write not A, and B is assigned a value of true, so we'll write B. Now, step 2 consists of creating a disjunction of all of the conjunctions. So we'll take our two conjunctions, A and not B. This is our conjunction from row 2, and we'll create a disjunction out of them. This is our conjunction from row 3. The thing to know here is that this formula is in disjunctive normal form, and it is false whenever the function is false. And this is not what we want. First, we want a formula that is in conjunctive normal form. And then second, we want a formula that is true whenever the function is true. So the way to get this, what we'll do is we will use one final step, which will be step 3 here. Now, step 3 will involve flipping all of the signs for disjunction with the signs for conjunction and vice versa. So whenever you have a sign for disjunction, this V here, you'll replace it with the and symbol. And whenever you have an and, you'll replace it with the V. And also what we'll do is we will flip the literals. What this means is you will replace propositional letters with negated propositional letters and negated propositional letters with just the propositional letters. So let's do that. So what we're going to do is, since we have A up here, we'll replace it with not A. Since we have this and symbol, we'll flip it so it goes from and to or. We have not B, so we'll replace it with B. Then we'll flip this or symbol with a symbol for and. We'll flip not A to A. We'll flip this and with or, and then we'll flip B with not B. The result here is a formula in conjunctive normal form. And this formula will be true whenever the function outputs a value of true. So what we've done is created a formula in conjunctive normal form for a truth table. So again, step one is to identify the false rows of the truth table where it outputs a value of false and create a conjunction where we write the propositional letter if the value assigned to the propositional letter is true, and the negation of the propositional letter if it's assigned a value of false. Then we create a disjunction of all of those formulas. This will give us a formula in disjunctive normal form. And then finally, the step 3 will be to flip all of the signs for disjunction with conjunctions, as well as flip all of the literals, replacing, let's say, A with not A and not B with B. Let me illustrate why this works, and for that, I'm going to use a simpler truth table. So notice here that this particular function is true in 3 cases and false in 1. Using our step-by-step method, what we would do is identify the false row, which is the 3rd row, and we would create a conjunction not A and B. Now notice something about not A and B here. The thing to note about it is when it is given this truth value assignment at row 3, what we have is 0, 1, 1, 1. We see that this formula comes out as true whenever the function here outputs a value of false. So the formula not A and B is true just in the case where the function is false. So if and only if the function is false. So what this would mean is that if we negated that formula, not A and B, well, this particular formula would be true. So this one would come out as true if and only if this function f. So it's this formula that we want to represent our function f, because this particular formula will be true whenever this function f is true. But notice one thing, that this particular formula here is not in conjunctive normal form. So with that in mind, let's actually put it in conjunctive normal form. So notice one thing about this formula, not A and B. It's a negated conjunction, so we can use De Morgan's laws on it, and it would give us this particular formula. It would give us not A or not B. So this would be by De Morgan's laws. Then if we were to use double negation elimination, replacing this not A with A, we would be left with A or not B by double negation. So note a couple things about this particular formula. The first is that it is in conjunctive normal form. And then the second thing to note is that this particular formula, A or not B, is true whenever the function is true, and false whenever this particular function is false. So going back to our 3-step process here, what we're doing is in the first step is creating a formula that comes out as true whenever the function has an input such that the output of that function is false. So notice that here that the function is false, but this formula would only be true given this interpretation. And this formula also, not A and B, would come out as true, but that function is false when it's given that interpretation. Now in our second step here, what we're doing is creating a formula that is true whenever our function is false. And then in our third step here, what we're doing is we are basically negating this entire formula and applying De Morgan's laws and double negation. And what that does is it gives us a formula that is true whenever the function is true. So this process of flipping the disjunctions and conjunctions and literals is essentially negating the formula and then using equivalence rules to find a formula that is true just when the function is true. Welcome back. So this concludes our discussion of normal forms in propositional logic. I want to conclude with a couple observations, or at least one observation. One question you might have is, well, why care about normal forms in the first place? Like, what's the point of all this? Well, that's a really good question. Generally what you see in, let's say, a logic textbook is the reason you want to put a formula into normal forms is that they are simpler. So the reason is mostly for human readability. So what does that mean? What does it mean for a formula to be simpler? What is meant is that the formula's truth conditions are easier to read. So let me give you an example of this. So take a look at these two formulas and notice that this second one is in disjunctive normal form. Now, the claim is that we can easily just look at this formula, which is in disjunctive normal form, and know the interpretations under which this formula is true. One way of putting it is that this formula wears its truth conditions on its sleeve. So how do I see this? Well, I see that, this particular formula line 2 is true provided either A is false or Q is true, or the interpretation B is true and C is false. So just by looking at 2, I'm able to read off the truth conditions of that formula, and I know what needs to be the case in order for this formula to be true. So that's generally what people mean when they say, well, if you put formulas in disjunctive normal form in particular, the formula is simpler or easier to read. Another thing is that if you can just see the conditions under which this formula is true, then you know that the formula is not a contradiction. And so you know something about the formula because it's so easy to read. In contrast, it's at least claimed that a formula like 1, which 1 and 2 are equivalent to each other, they're true and false under the same situations. It's not immediately obvious what would make the formula in number 1 true, and so it might not be immediately obvious that this formula is not a contradiction. Another reason it's helpful to learn about normal forms is because essentially you're learning the fact that the operators for conjunction, disjunction, and negation are truth functionally complete, or sometimes said to be adequate or expressive. What this means is that you can take every truth function and express those functions just using those operators. In other words, you don't really need the right arrow or the biconditional. You can dispense with those because you can express every truth function just using the and, or, and not. So hopefully you found this video helpful. If you have, let me know. If you have some kind of point of further clarification, I'd love to hear that as well. And so thank you very much for watching.